Hello, everyone. Very good morning, good afternoon, good evening to all the attendees from world over. I hope and pray you all are fine and keeping yourself safe. Welcome to this, as we say, a very thought-provoking panel discussion on COVID-19 and indoor spaces. We have a panel comprising of the best minds from the industry and domestic and international. My name is Nivedita Jadhav. I'm a member of the ISHRAE Standards Committee and Vice President at ISHRAE Mumbai chapter. Before we begin the session today, let's briefly take a look at what ISHRAE is all about, because there are quite a few international participants and I would like all of them to know about it. So ISHRAE is the Indian Society of Heating, Refrigerating and Air Conditioning Engineers. This was formed in 1981 at Delhi. ISHRAE today has a presence of in over 44 chapters and sub-chapters across the country. With the student fraternity, we have around 150 student college student branches. They are engineering as well as architecture. 27,000 members across the country with around 114 international members. Next. On the technical front, what ISHRAE has to offer is 40 plus publications, which have around already 10,000 circulation. Technical groups, which we started around a few years ago, they are already 30 in number. And there are 1,500 volunteers as of now. That's in a very short span, quite a number. The ISHRAE journal started in 1998. It's a bi-monthly publication sent by mail to all, as well as now it's in the soft version. So we have 15,000 downloads of the journal, along with 1,200 plus articles that have been published. A weather data book, which is for 250 cities across India, including our neighboring countries, Sri Lanka, Bangladesh, and Nepal. We have not been behind in the standards. Our ISHRAE environmental quality standards started, it's already rather in the second version, which was launched last year. We have a VRF standard and the chiller standard. Besides that, the recently launched air handling unit standard and a commissioning process standard. On the research front, we have already invested 12.3 million rupees on the research projects that have been going on for the past couple of years. On the student projects, which our student chapters have, for the past 10 years, we've had around 500 plus projects that have been funded. We have the ISHRAE certification courses. These are 5 in numbers and 1 4-month diploma course. So besides this, of course, we have around 1,600 or so programs done every year by chapters and sub-chapters. So with this, I hope we can get many more members from the audience that year and feel attracted towards ISHRAE. Now, let me get on to the session by inviting our National President, Mr. Amitabh Basur. Can we have Amitabh Basur take the platform, please?
Yeah, hi, Nivedita. Thank you. Hello and namaskar, friends. I heartily welcome you to this panel discussion on COVID-19 and indoor spaces. The annual theme of ISHRAE this year is Lakshya. Lakshya is actually a Hindi or a Sanskrit word. English meaning of it is goals or targets. So Lakshya is also used as an acronym in the ISHRAE theme. So it's spelled as LAKSHYA, where L stands for lifelong learning, A for adopt best practices, K for knowledge enhancement, S for share and serve, H for harmonious growth, Y is yearn for excellence, and finally A for accomplish. So in line with that theme, the learning, adapting best practices, knowledge enhancement, which we want to do, also sharing the members with the members and serving the society at large is that is the reason we have arranged this panel discussion today. And it's on a very current and relevant issue, not only for air conditioning engineers only, but also for users. There was a lot of dilemma in our mind, whether to use air conditioners during COVID, if to use, then what are the precautions to be taken? What is the best ways to kind of mitigate the risks in the indoor spaces? We have heard of more, taking more outdoor air, improving filtration levels, but how to do it in existing installations, blah, blah, blah. So today's panelists, friends, are domain experts on these, and they will certainly help us understand better the best practices that needs to be adopted while designing an air conditioning and ventilation system today. So I'm excited to listen to them and to learn from them, and particularly more because I'm aware our moderator Vishal Kapoor has come with his guns loaded. But I'm sure our learned panelists will happily chest those technical bullets from Vishal's technical gun. So I'm not going to keep you waiting further. I hand over the platform back to Nivedita to press the start bell. And please feel free to ask your questions on the question box. Vishal will appropriately take them. And most importantly, friends, please take care of yourself, stay safe, and stay healthy. Thank you. Namaskar.
Thank you, Amitav. Now, just before I draw over away the curtains from this session, I just want to inform you all that we will be sending all the handouts of this presentation by email to all the attendees, so you all can concentrate on this session. So now, to welcome our moderator of the day, Vishal Kapoor. Vishal Kapoor is a BTech Mechanical Engineering from IIT Roorkee. He's done his MBA from FMS Delhi. He's the Managing Director of Mehu HCP Air Systems Private Limited. He's also a partner in Environmental Protection Services Company, a firm offering HVAC remediation and IAQ services. For ISHRAE, he's been the national president in the society year 2017-18, national chair technical committee for the past 3 years, and the COVID task force chair, and also a board member of the Indoor Environmental Quality Global Alliance. So over to you, Vishal. Thank you so much.
Thank you very much, Nivedita, and a warm welcome to our audience from across the globe. Good morning, good afternoon, good evening to everyone. It's a wonderful day. And we've been talking about COVID now for the last 15 months. We hope we never had to talk about this, but then the reality is in our faces. This pandemic has disrupted the lives of all of us in many ways, but it has also presented us opportunities to learn and change the ways we live. It has taught us not to take humanity and science for granted. We've hopefully learned the value of research and knowledge and the implementation of it. COVID-19 has compelled us to confront our limitations as a species, and yet we have risen to the challenge to bring out tests, vaccines, treatment protocols in such a short time. The number of active cases have surely gone through waves, but the total cured numbers globally do give us some hope of the future. Specifically to our own country, India, we are facing a very strong wave, the second wave, which is very severe. But at the same time, we have conducted 370 million tests. The numbers are staggering for people listening in from the globe. 370 million deaths. The death percentage is surely going to go down in the days ahead because the world's biggest ever vaccine program is underway. 240 million doses have already been given, which is possibly larger than most country populations and adding up to 12% of the world's vaccines till date. Travel and face-to-face meetings have surely reduced, but the world has become closer, working together, supporting each other with resources of knowledge, technology. There are going to be some permanent changes in our lives post-COVID, and one of the biggest impact areas would be in the design and usage of indoor spaces. Most infections of the virus have occurred indoors, and this has forced the world to ask questions of how safe are our indoor spaces? How can we reduce the spread, if at all we can? The amount of time people spend in a closed environment matters, and the greater the number of people in an enclosed space, the higher the odds that one of them is going to be contagious. As it is, we spend 80-90% of our time indoors, and during lockdowns, even much more, whether in the residence, office, school, shop, restaurant, air-conditioned or not. The airborne nature, the confirmation of the virus being airborne, has further caused a panic, leading to doubts regarding the design and operation of HVAC systems, whether this helps in the spread or reduces the same. There have been incidents of people not wanting to open their house windows, fearing that the virus might come in, thinking it's airborne. There are others who are advising, do not turn off an air conditioning, keep it off if you want to be safe. All kinds of things are going around us. At the same time, we cannot ignore the importance of HVAC, as humans need thermal comfort and a good air quality for all aspects of life, work, leisure, rest, or play. In fact, it is HVAC that can also mitigate the spread of this and other infections in the future, as long as we know what to do and how. Since February, March last year, most of the leading technical organizations globally have been working hard to bring out guidelines on operation and maintenance of HVAC systems and technologies, good practices to mitigate the spread. We at ISHRAE also brought out several documents for the same, covering all kinds of applications, including healthcare. This found phenomenal acceptance with the statutory authorities, facility managers, designers, service providers, property owners, users, etc. The guidelines centered around 5 principles: indoor conditions, ventilation, filtration, airflow management, and maintenance. Our guideline also addresses specific applications like residences, offices, and industry, factories, including operations protocol to reopen post-lockdown. Good practices for technologies such as evaporative cooling was also presented, as also non-AC applications using fans. The document covered safety protocol for the service engineers and technicians in the field. Subsequently, we also launched guidelines for operation of air conditioning systems installed in healthcare facilities. This was done jointly with the Indian Medical Association, IMA, and we covered surgical operation room, quarantine, intensive care units, patient ward, chambers, diagnosis centers, clinics, general areas in a hospital. In spite of all these efforts globally, within India and all over the globe, unfortunately, Indian air quality has not received the due importance it deserves. And we all wonder why standards and codes have not been mandated and taken as seriously as, say, water. Safe water for all. What about safe air? Not just outdoors, as the indoors is 10 to 15 times more polluted. But possibly the last year has made people sit up and ask questions. In the process, multiple solutions, products, technologies have been suggested, all of which might not be right, technically or economically or from a health perspective. We should not implementing a solution which might solve one problem but create 2 others. COVID hopefully is temporary, but good IAQ will always be needed. Please remember, a building is all about people, and of utmost importance is their health, safety, and comfort. Also, in the process of changing design, using new technologies, products, etc., we should not forget that the most important aspect of controlling such spreads and improving IAQ is source control. And that has to be the first step always. To cover these topics and more, we are pleased to have a panel of experts with in-depth knowledge, rich experience, and detailed research over the last years maybe in this subject. The presentations and discussions will reflect on their experience from a spectrum of perspectives and knowledge updates. The presentations will focus on the most critical recommendations or solutions, which are airborne infection, ventilation, air cleaning, airflow management, humidity control, IAQ monitoring, and finally HVAC design for fast-track healthcare facilities. Each speaker shall start with a short presentation on a specific subject, and subsequently we will have 1 hour or more of relevant questions being shown at them. If you have any questions which are not addressed in the presentations, please feel free to enter them in the questions box. Please do not repeat a question which has already been asked by somebody, or if it has already been addressed in the presentation. Also, please note that we are not going to get into detailed workings of any technology. Please keep it a little bit more generic in nature, because we would not have the time to get into a deep down dive into any subject. We can always have that at a later date. Please do remember that the final solution is a mix of various practices and protocol, and no one size fits all. So the first speaker I would like to invite does not need any introduction, but for formality's sake, we would do that, is Dr. William Barnfleth. Our friend Bill, one of the most active persons in this field over the last 15 months. Bill, could we have you on the Zoom hall?
My video's on. Do you see me?
Yes,
okay, there we are.
Absolutely, there you are.
All right.
There you are. So Bill is a professor of architectural engineering at the Penn State University, Pennsylvania State University, to be made it clear if I'm right. Has held previous positions as senior consultant for ZBA Incorporated, principal investigator at the U.S. Army Construction Engineering Research Laboratory. He holds a BS, MS, and a PhD degree in mechanical engineering from the University of Illinois and a registered professional engineer. His research interests cover a wide variety of indoor environmental control topics, including chilled water pumping system, stratified thermal energy storage, protection of building occupants from bioaerosol releases, and UVGI. Co-author of more than 170 technical papers, articles, and 14 books and book chapters. He's a fellow of ISHRAE, fellow of ASME, and the International Society for Indoor Air Quality and Climate. Served as president of ISHRAE in 13-14, currently chairs its epidemic task force. His ISHRAE honors include the Lewin Bill Holiday Distinguished Fellow Award, E.K. Campbell Award, and the F. Paul Anderson Award. Recipient of the Penn State Engineering Alumni Society's World Class Engineering Faculty Award, and a Penn State Exemplary Designation for Faculty Outreach. Bill, over to you to take it on the subject of airborne ventilation, airborne infection and ventilation. Thank you. There you go.
Yeah, thank you very much for the kind introduction, and I'm glad to be here with everyone. I appreciate the large audience. My talk today is going to cover just the bare basics of transmission of COVID-19, and then the most fundamental of engineering controls, ventilation with outdoor air. That hopefully will set the stage for the others. One of the things that's been a prominent feature of the last 15 months has been the debate over whether COVID is airborne or droplet transmission, using the terminology from infectious disease epidemiology predating the pandemic. And it's been a very costly debate between a number of parties, including public health organizations and aerosol scientists and public health experts and engineers. If we go back to last March or April, WHO and CDC in the US were very strong in their statements that by their definition, COVID wasn't an airborne disease, but at the same time, we were already seeing papers like the one shown here, written by Lydia Morawska and Junji Chow, that were pointing out reasons why we should believe that COVID could be airborne. And so that went back and forth really through all of 2020. And it wasn't until May of this year that WHO and CDC both made statements that were clear about the potential for airborne transmission. Why is this important? If you believe that the transmission is due to large droplets at close distance that are striking your eyes, nose, and mouth, and that's how transmission occurs, then one set of protections is warranted. And if you believe that there is significant risk from inhalation of small particles, then another is warranted. So the two roads diverged in a yellow wood analogy. So for a long time, public health authorities were promoting droplet transmission protections that limited the use of high efficiency masks and that focused on cleaning and distancing, and there was not very much emphasis on measures to reduce inhalational exposure at a distance. That there is now a very large body of information that supports the idea that inhalational transmission is perhaps the most important. Basic aerosol dynamics are one argument. Historically, 5 microns has been viewed as the distinction between a droplet and an aerosol, something that could travel a long distance and something that would fall quickly. That's simply not true. And then we have studies that have found SARS-CoV-2 RNA in aerosols and actual active virus in aerosols, and other research has shown that the virus can be active in the air and on surfaces for periods of hours to days. So all of the fundamentals are there. And then we have a large number of case studies, of which I've only listed a few here. The Guangzhou restaurant that's been investigated extensively, and the Skagit Valley Choir Rehearsal in the US, and more recently the Sydney church service case that have all, when investigated, essentially ruled out the likelihood of close contact or fomite transmission, intermediate surface transmission by touching, being the cause. In the Guangzhou restaurant, which now has 2 very good papers published about it, we saw transmission in a poorly ventilated restaurant where 9 diners were infected, and they were at distances up to nearly 5 meters away from the infected person, and video evidence rules out the likelihood that there was transmission by fomite in this case. Much more recently, there was an article published about a case in Australia in a church service where one infected singer on 2 different occasions infected 12 persons. On the right, you can see the plan of the church, and the red dot is where the infected person was standing, and in 2 different cases had a large number of infections caused that certainly can't be due to any other cause than airborne transmission. So we have that evidence, and this very vigorous dialogue has actually, it seems, changed the terminology that we use to describe infection transmission. The old list was droplet, airborne, or fomite, and the assumption was that if it was close contact transmission, that it was these large droplets, and that aerosols were only relevant far away. A lot of good research that's been done in the last year has showed conclusively that a lot of the exposure, even at close range, is by inhalation of aerosols. And so when the CDC in the US came out with its updated statement on transmission in May, they put at the top of the list inhalation of fine droplets and particles, and now they're calling what used to be droplet transmission deposition from splashing or spray onto eyes, nose, or mouth, and fomite is at the bottom of the list and described as touching. As time has gone on, the likelihood that there has been significant transmission due to touching or fomite transmission has decreased steadily. There are really no good studies that show that there have been serious outbreaks as a result of that. The figure on the right comes from some of Hugo Lee's work and shows how these definitions relate to one another. We can have aerosol transmission at short distance as well as spray, but we can also have distant inhalation where droplets are not a factor, and touching can occur either directly from an infected person touching another, or it can be through an intermediate surface. And importantly, this new definition of large droplets is more like 100 microns or larger. Smaller droplets in strong air currents can move surprisingly long distances. So what are the means for reducing risk of transmission? Some of them relate to buildings and building systems, others don't. Distancing, face coverings, hand hygiene, reduced occupancy, reduced occupant density are all things that can help and have helped during the pandemic. Today, we're talking mainly about the engineering controls, ventilation, mechanical filtration, and air disinfection. So ventilation is our most fundamental indoor air quality control. It simply involves bringing in outdoor air that we believe to be less contaminated in some sense than the indoor air, and using it to dilute contaminants, and then contaminated air is exhausted in equal volume. This can be mechanical ventilation, so brought in by an HVAC system using fans, or it can be natural ventilation from openings in the enclosure of the building, but the effect is the same. Although the effectiveness may be different from one method to another. And air distribution here is very important. That'll be talked about later, but we have a range of ventilation delivery techniques that ranges from personal ventilation, where we supply clean air to the place where someone is breathing. More commonly, most ventilation is mixing ventilation, where we generally mix cleaner air with the air in a space and get more uniform concentrations of contaminants. And there are more efficient methods like displacement that put the cleaner air into the occupied zone and push contaminants up and out. So there's a big impact here of how air is distributed that you'll hear about later. But what about the rates? How much outdoor air do we need to bring in? The current rates in non-healthcare facility design are based on controlling some known indoor health risk contaminants like VOCs, and also controlling odors. And there's a moderate particulate filtration requirement that goes along with that. So ISHRAE standard 62.1, for example, puts us at about 15 CFM or 7.5 liters per second per person, maybe 1 to 3 air changes per hour if we view it that way, and MERV filtration. And this certainly isn't very effective for infection control. This has been well discussed. If we look at healthcare facilities, they have higher outdoor air supply requirements typically, and higher recirculation requirements through high efficiency filters, which is very important. ASHRAE standard 170 deals with healthcare facilities, and typically the outdoor air is 2 to 4 air changes per hour, with a total supply of 6 to 12 air changes per hour, with pretty high efficiency MERV 14 filters, or even up to HEPA for some types of facilities. The recommendations based on risk assessment for COVID have typically recommended total clean air delivery rates of 4 to 6 air changes per hour. You can see in the figure on the right that historically we've had a hard time deciding what we want to do with ventilation. If we went back 100 years, we see typical ventilation rates of 30 CFM per person, which actually could have some significant impact on health. And for energy conservation reasons, we've been as low as 5 CFM within the last 50 years or so, but most of the time floating around this 15 CFM or so odor and basic health protection limit. So if we want to have ventilation rates that will protect us against infection risk, we have to do some kind of a risk assessment. During the pandemic, the Wells-Riley model has been used extensively. It's been extensively criticized too, but it's the one that we have, and it's been helpful to do at least some level of risk assessment. So it predicts the percentage of new infections in a space on the basis of the source strength, so the number of infectors and the rate at which they're producing infectious doses or quanta. This can be affected by their activity level, by whether they're wearing a mask or not, and then also the uptake of contaminated air by the susceptible, which depends on their breathing rate, which also means their activity level and the time that is spent breathing that air. And those both increase risk. Uncontaminated airflow into the space can reduce concentration and reduce risk. So we can use this to develop requirements relative to certain risk targets. And it's important to point out that uncontaminated air doesn't have to come from outdoors. It can come from filters or air cleaners as will be discussed. We have infectious quanta numbers that are being used for SARS-2, but they're pretty smudgy in terms of their accuracy, two orders of magnitude between the 5th percentile and 95th percentile. And we can see in this figure on the right that the quanta number that you choose has a big impact on risk. So we're doing the best we can, but could do better. And just in general, if we look at reviews that have been done on ventilation, we certainly know that there's a relationship between ventilation rate and infection risk, but the conclusion of some pretty careful literature reviews that have been done in recent years, like this one by Lee et al., have concluded that there's insufficient data to specify and quantify the minimum ventilation requirements in relation to spread of infectious diseases via the airborne route. So we still have some work to do. So to summarize here, we've been debating for a year and now agree that SARS-CoV-2 is airborne. Therefore, we should be taking airborne precautions to reduce this inhalational component of exposure, which is very important. Ventilation is just one way to lower exposure, and its effectiveness is strongly impacted by air distribution. And another concern about it is that increased outdoor air will cause higher energy demands on buildings and also can affect energy use and comfort. So it's not necessarily the first recourse to increase ventilation a lot. Ventilation plus uncontaminated air supply from other sources is probably a better approach. And then finally, to reemphasize that we have a lot of work to do to define what appropriate ventilation rates are for infection control. And ran over a little bit, but hope not too badly. And that's all I have to say. Thank you.
Thanks a lot, Bill. I think in your time slot, I know it was not doing justice to cover two big items of airborne infection as well as ventilation in a short span of 10 to 12 minutes. But I think you pretty much summarized it very well, and saying that the importance of ventilation to control the infection is only one of the solutions. It's not the only solution, which a lot of people have this concept that if I ventilate, that's good enough. And that is why we organized a presentation like today, where we are talking of all the possible options to ensure the spread is reduced or mitigated to a large extent. So thank you for starting it off. And there are a lot of questions which I already have, and some are being asked. I think we take up the questions to comment towards after all the speakers have finished their presentations. So thank you, Bill. And absolutely. We would now like to invite our next speaker, Dr. Marva Zatari. Marva is a PhD in architectural and environmental engineering from the University of Texas at Austin, a master's degree in engineering management from the American University of Beirut, Lebanon, with a focus on energy management, a partner in design partners and a co-chair of Embedded Systems Advisory Board, IAQ 2020 conference organizer, a lead committee member, also serves on the US GBC board. For ISHRAE, she's a distinguished lecturer, a member of the Epidemic Task Force, voting member of the Standard 62.1, chair for TRG for Indoor Air Quality Procedure. Sorry, I had to cut short your profile. Otherwise, I would have taken up half of your presentation time only reading out your profile. So welcome, Marva. And I know you're going to be talking about a very interesting topic. It's air cleaning. 10 minutes is nowhere near sufficient to cover all kinds of air cleaning options. But nevertheless, we'll see what best we can do. And then we can obviously address more of those questions. So over to you, Marva, to take it on from there. Thank you very much.
Thank you so much. And thank you for all the attendees. I'm very excited to present this topic. So I'm going to talk about air cleaning. And this is the agenda. I know I have short time, so I have 10 minutes and 5 questions. I'm going to start with the ISHRAE recommendations. I'm going to talk about MERV, HEPA, what are some considerations for in-room air cleaning, requirement for UVGI, and then what is the state of science regarding electronic or additive air cleaners. Starting with ISHRAE recommendations, when it comes to filtration air cleaning, ISHRAE recommends the use of one or combination of filters and air cleaners to achieve a MERV 13 equivalent or better level of performance of air cleaning. So you can use one or multiple to achieve MERV 13 or equivalent. The only thing here is that you need to use proven technologies. And ISHRAE definition of proven technology is that technologies where we have sufficient evidence of effectiveness and no harm. And I have a quick checklist when I evaluate these technologies. First, is there a standard or guideline that I can use to understand what are the test conditions, and more importantly, how they translate to realistic or real life conditions? The second one, in case of an emerging technology, is there sufficient peer-reviewed data that found the same finding what the manufacturer published? And the last one, which I think the most important, do we have enough, do we know enough about safety? So there are some things that we look for, and we know, for example, do the device generate ozone or some VOCs or ultrafine particles? We know how to look for this, but also there are things we don't know how to look for, and we don't have yet studies. For example, what is the no harmful level of ions or specific chemicals? I'm going to talk about this a little bit later. But first, I'm going to start with mechanical filters. When we talk about mechanical filters, I refer to media with porous structure or basically stretched membrane to remove particles from the air. The fraction of particles removed when air goes through a filter is called filter efficiency. And we have an ISHRAE standard 52.2, and also we have international standard like ISO. But ISHRAE standard 52.2 has a specific rating. It's called MERV, minimum efficiency reported value. And it gives you, among other things, efficiency by particulate size. So MERV goes from 1 to 16. I still see until today, some like big box retail stores or online, you still see MERV 20. MERV 20 does not exist. In the ISHRAE Building Readiness Guide, we have a detailed explanation of how to calculate efficiency and what is the assumed particle size distribution. As a summary, MERV 13 on average is 89% efficient. And it's not 1 or 0. If you still use MERV 11 or MERV 8, they have some efficiency for the virus. I'll explain a little bit later, but imagine this. MERV 13 is the most cost-effective solution, so it's cheap. We probably can install it in our building, and it's very efficient. Since most of the air is recirculated in our building, pass it through, and a very efficient filter will give us like a large portion of the air exchange rate we're looking for. As everything else, it needs to be properly designed, spec'd, and installed. We talk about pressure drop. Is my system able to handle the pressure drop from the MERV 13? Can I seal it very well? And the seal and the fit is really important for the filter. When you put it, the gap between the filter and the air handling unit need to be minimized to basically practically 0. And lastly is that we need an airflow to go through the filter. So if we talk about residential system or other system that cycle on and off, you need to make sure that if possible, to keep the system on during the occupied hours, so you have constant removal of the particles. And by proven technologies, this is a proven technology because we have ISHRAE standard, among others, that basically give you efficiency by particle size and also pressure drop. So you're able to take the data from each manufacturer or distributor and apply it to your specific system. Specifically in the graph that shows the efficiency on the y-axis, on the x-axis particle size, you see the shape of the graph is an inverse bell curve. Make note of that because I'm going to talk about it when I talk about HEPA filters. One of the things I encounter personally is the notion when people say, oh, we cannot upgrade our filter because we're going to choke our system. We're going to reduce the airflow. I'm going to damage my system. And we're going to increase energy consumption. That might be true, but not necessarily true if you do your homework. I show you this work. On the y-axis is the pressure drop. On the x-axis is 3 different MERV category, 8, 11, 13. And the different blue diamonds refer to different manufacturers. I show you here that you can have a MERV 13 filter that have equal or lower pressure drop than a MERV 8. So if you do your homework and you ask for the specific data and apply it, not necessarily you're going to choke your system, and not necessarily you're going to increase energy consumption. Moving on to HEPA, which stands for high efficiency particulate air filters, but HEPA, not HEPAF. By definition, HEPA filters are at least 99.97% efficient at 0.3 micron. And also they have to be individually tested for efficiency and also for leaks. And I've seen some manufacturers start to put a label on each filter to say, you know, what is the actual efficiency? Another form of a proven technology. But one thing I wanted to highlight about the inverse bell curve, you see it as well with the HEPA and the MERV graph I showed earlier. There's a notion that I'm hearing a lot about it since the beginning of this pandemic, is that, oh, since HEPA filter is specified at 0.3 micron, it's not able to remove below 0.3 micron, and the virus is so small, so HEPA do not work. This is a false statement. We know for a long time, since the Manhattan Project, since the creation of atomic bomb, is that the smallest size is that particulate size between 0.1 micron to 0.3 micron are the most difficult to remove. So if you see the inverse bell curve, you see like below 0.1 micron and above 0.3 micron is very efficient. The dip happened between 0.1 micron and 0.3 micron. So HEPA are specified at 0.3 micron or the most penetrating size. It might be a little bit less than 0.3 micron because they are the most difficult particle to remove. Same thing for notion for MERV. The other thing is that, and the reason why MERV 13 is very efficient is, although the virus size is so small, but when we cough, we sneeze, we talk, we generate particle size much bigger than 0.1 micron. Can be most particle size distribution is above 1 micron. And this is why MERV 13 is very efficient. Now moving in the same line for HEPA, can be installed in HVAC system, but if your system is not designed for HEPA, probably it's going to damage your system because of the high pressure drop. What we've seen is that HEPA filters are specifically used in portable air cleaning when we talk about commercial building. Actually, in-room air cleaning, because it can be portable, as you see on the top picture, or fixed. It can be fixed on the basically the wall or on the ceiling. And I did this homework when I was trying to look for my house and my son's school for HEPA in-room air cleaners. The very important thing here to note is that you only need a HEPA filter and a fan. You can have a sensor, you can have display of particulate matter concentration, that's fine, but make sure that you don't have any of other things that we don't understand, like for example, ionizers or a UV light that's shining light on a catalyst or some hydrogen peroxide, for example. So it's very important to know what you're paying for. So if I'm paying for a HEPA filter, I want to get a HEPA filter. So I summarize here some of the things that I found that, manufacturer will say that it's a HEPA, but it's not actually a HEPA filter. Like they use terminology like HEPA type, HEPA-like, near HEPA, HELPA. Some of them, they don't have a HEPA filter to start with. Like for example, a HEPA silent is actually an ionizer with a small pleated filter. The other thing, just to pass it through very quickly, I saw also plants being marketed as air purifier, and from Dr. Richard Corsi research, they do very, very little. They look nice, but they do very little. So definitely not for COVID. There are some consideration when using the in-room air cleaners. We start with the space size, layout, airflow distribution. I know Dr. Kishore is going to talk about airflow distribution, but basically, what is the room size, height? What is the layout of the room? Can you put it in a way that you have access to power and also no safety issues, and you ensure a good airflow distribution, like the clean air is not going to go, for example, to be exhausted or deflected. Second one is noise, and this is extremely important depending on the space type. But we know from history is most people do not use, for example, the range hood because it's noisy. So it's very important to look at the noise at the highest efficiency. What we call it is the clean air delivery rate. So clean air delivery rate is a terminology approximately equal to airflow times efficiency, and it's from AHAM, the Association of Home Appliance Manufacturers. And then you can calculate an air exchange rate. And this is a very nice metric because you can compare different models and you can know what you're paying for. Again, it's important. What is the cost of the air cleaner, replacement cost, and what is giving you in return? A metric that I like to use all the time is called dollar per risk reduction, or dollar per air exchange rate, or dollar per clean air delivery rate. And I show you here at the end of the slide an example of how much each clean air delivery rate will give you an air exchange rate. And I have in the extra slide a review of many different manufacturers in terms of efficiency and in terms of cost. But basically, you have a lot of options. A quick word about UVGI. UVGI is another proven technology. I know Dr. Bamflet did a lot of work about this. The recommendation from ISHRAE about induct, so the one you put after the cooling coil, is to have 1,500 microjoule per centimeter square. And this is a conservative estimate that takes into account many factors like temperature, humidity, aging of the bulb, the soiling of the surface, and the airflow and the air exchange rate. Now, remember, like the ISHRAE recommendation is one or combination of filters. So I'll show you how to do the math. One client was saying that they have MERV 16 because they have MERV 8 and MERV 8, so double stage filtration. This is not the way to do the math. Fortunately, ISHRAE published an open source tool to help you to do an addition of several technologies. And here, just an example. So if you cannot use MERV 13, you're not doomed. There is a lot of things you can do, like addition of UV, or for example, having in-room air cleaners, and you can mix and match between the different technologies to obtain MERV 13. My last topic of today is electronic air cleaners or additive air cleaners. Unfortunately, even we don't have a name for these, like a terminology, but there are 4 broad categories and many different names because we don't have any type of regulations. We talk about photocatalytic oxidation, like it's air, UV light shining on a catalyst, dry hydrogen peroxide, ionization, oxidant, like for example, generation of ozone, and fumigation. But the mechanism, although they are very broad category, the mechanism is the same. They add something to the air to subtract. So they add like reactive oxygen species, ozone, radicals to subtract. So to have a chemical reaction to remove something. The fact is that indiscriminate and unpredictable reaction will happen. And these technologies are unproven in the same definition I basically explained before. they're unproven to be safe or effective. And the reason why I say that is that we don't have a standard and a guideline. So as engineers or users, we don't know what to do in order to specify for a specific room size, height, temperature, humidity, airflow. What is the specific ion count correlation with efficiency? How far is the instrument is put? Is it in room? Is it in duct? Is it in the air handling unit? What is the effect of the length of the duct on basically the output? And we have emerging research. I didn't cite them here. They are cited later in my extra slide that show basically that some ionizers, that basically the efficiency is negligible. Some of them, they do something, but some of them negligible. And some of them, even though the manufacturers say they don't produce byproducts, produce actually VOCs, ultrafine particles, and ozone, even though the manufacturer will have a zero ozone claim. The last thing I want to say is that I worked with the researchers in 3 different universities to produce an open source tool to help you decipher what the manufacturers say versus what is the realistic efficiency. I'm not going to go through it, but basically this specific manufacturer will say that they have 98% efficiency in removal of COVID in air. If you put it in this calculator, the air exchange rate is 0.3 air exchange rate per hour. You know, Dr. Bonfles mentioned air exchange rate recommendation between 4 to 6 air exchange rate per hour. So you see this device, although costly, will do very little. To achieve 5 air exchange rate per hour, as specified by this device, you need actually 64 devices, 64. My summary is that stick with the proven technologies. We know they work before COVID. We know they're working during COVID. And more importantly, they will work after COVID. We talk about mechanical filters, HEPA, and UVGI, in addition to what Dr. Bonfles said before about ventilation. Thank you so much.
Thank you very much, Dr. Marva. I think the subject, air cleaning has been one of the most, if I may use the word controversial, specifically over the last year and a half, because of the scare, the panic, and so a lot of technologies and solutions coming in the market, which you rightly said have not been really tested or proven till now. But yet they keep on coming out and people are buying at risk or not, effective or not, is something which I think time only will tell. But it is a most important subject of air cleaning, because till now we were all just bothered about media filters and UVGI, and now it's a different line of word altogether. And also this open-end tool of putting filters together to get the effective filter rating is also something that is very important for retrofit projects, because where people want to improve the filtration levels, this is one way of actually looking at what they are putting in. So thank you very much for addressing this very, very important topic. And we will be coming back to you later with a lot of questions which are directed your way. And we'll see how best, whatever time we have, we can look at that. Thank you very much. I would now like to welcome Dr. Kishore Khankhari. So we have diluted the air, sir. We have cleaned it. We know to ensure it flows in the right manner. So it's a good job that you have in your hand. Dr. Kishore is a PhD in computational fluid dynamics from the University of Minnesota, president at ANSITE LLC, a specialist in CFD, a member industry advisory board for architectural engineering, the discipline of Lawrence Technology University, a proud ISHRAE member. With ISHRAE, he is a DL, a fellow award, a distinguished and exceptional service award, leads a multitask group on air change rates. Also very recently nominated as a director at large on the ISHRAE board. Welcome, sir, and a very important, and I would openly say it, a very neglected subject on air distribution and airflow, because most people believe just throw in air, if it's cooling, we're happy, and not bothered about anyone else. So over to you to take this subject from here on.
Thank you, Vishal. Thanks for your invitation for me to participate in this esteemed panel. In fact, you introduced the subject so well, I don't think I need to speak anymore on this one. My message is very simple. Airflow patterns in indoor spaces matter. Everything matters. How you bring the clean air, how you clean it, whether you have UVGI in the room or in a duct, air cleaner in a room. At the end of the day, how air flows indoor spaces is important. So why does it matter? Air is the primary carrier of heat, moisture, and airborne contaminants. We who work in HVAC industry, we are fortunate that we are to work with only air as a fluid and not worry about most of the other time, the other fluids. That's why understanding the airflow pattern in indoor spaces is very important, because what path airborne pathogens take or airborne contaminants take, it depends on how air moves within the spaces. So the high level ventilation strategies, as we know, it's the containment, pressurization, which is often used in the healthcare facilities, positively or negatively pressurized rooms, so that the zonal transport of contaminants from one room to other, or room to the corridor, or corridor to the room is minimized. The one which is very popular, very well studied, is the dilution philosophy, where you bring the clean air, you have contaminants in the space, and you can dilute it to the acceptable level so that you can reduce the risk. And more air you bring it, more dilute the atmosphere would be, the indoor air would be. The last one, as Vishal said, not too many people pay attention to, is once you bring the clean air and once it becomes dirty, we need to remove that so that we can effectively create the good environment in indoors. So that is often neglected part. And I'm going to talk more about that part. About the dilution philosophy, this is very well-known equation that if you know the generation rate of contaminants, and if you know what is the acceptable level of concentration that you need, you just divide G by C and you will know how much air you need. Well, there are several things in this equation. First of all, do you know what is the generation rate? As Bill pointed out, what are those quanta for? We don't know. There are all those spaces. And then what is the acceptable concentration? Not much is known, leave alone COVID situation, but for other contaminants, there are different values for that. So what engineers do, they use that safety factor. And that safety factor really overrides all the basic equations, G or C. Those factors are so large that sometimes I question, why do we need this equation? And most importantly, all these theories of dilutions over the years, over the decades, have been developed thinking that the space is well mixed. As if this is your cup of tea and you add sugar to that and stir it, and momentarily it becomes a sweet tea. The room is not like your cup of coffee or tea. It's a large space, there are several things in the room. And so achieving a well-mixed concentration in the spaces, to my opinion, is a myth. You try very hard and you can't get well-mixed concentrations into the space. So this is slightly a side topic here, is the air changes per hour. In India, we call it ACPH, air changes per hour. Here in US, we call it ACH. Very well talked terminology. People use this left and right without understanding why are we talking in terms of air changes per hour. Why not we just say how many CFM, how many meter cube per second, how many liters we are putting into space. We divide it by the room volume. So this is a double-edged sword. What it does is definitely tells is how much you are going to dilute, because the air you are bringing in, it's just in the numerator, higher the numerator, more the dilution will be. One other thing that is often not understood is when you say in terms of air change rates, what you imply by that is how fast you want to clean the room. And more often, when you purge the room, the sources of contaminants are not there. For example, people leave the office space and then they say, you purge the room. It means, assumably, there is no source of contaminant. People who are breathing out germs are gone, and we want to clean the space, the purge the space. So This is another important aspect of air change rates when you talk in terms of air change rate, because the volume of the space acts like an inertia. Larger the space, more air you will need to clean it faster. What this does not tell you, and that is the topic, is how well you are cleaning the space. It is not how much air you are bringing in, it is how well you are cleaning the space. And what Amitabh said is the lakshya. The lakshya of ventilation is to bring the clean air to maintain the desirable indoor quality. So these are some of the components. You can see the clean air comes often from a four-way diffuser. Clean air, I mean uncontaminated air. There's again a debate about what you call it clean. And then there are occupants. Of course, it's an occupied space, and they breathe in and breathe out. And in the COVID situation, they may breathe out some pathogens, COVID pathogens, into the space. And then this clean air touches the sources and occupants and kind of gets dirty, if you will. Now, this dirty air has to be removed from the place. You cannot just circulate the dirty air for long, then your effectiveness of cleaning is going to go down. What is important in all this discussion is the breathing zone of occupant. You may keep your ceiling near the roof, it is very clean, or your floor is clean, doesn't matter. We all breathe. What I call is the breathing zone, which is generally 4 to 6 feet height from the floor. So we have to pay attention. What is the indoor air quality in the breathing zone of the occupant? It doesn't mean that other spaces like above and below the breathing zone, they don't matter. They do, because they will bring the contaminants into the breathing zone. But our criteria should be in the breathing zone. Various factors can affect how well you ventilate your space. Location and number and type of diffusers, supply air flow rate, especially the discharge velocity from the diffusers, type of diffusers, location and number of exhaust or written grills in your space, location and extent of heat sources, because we generate heat. There are other heat generating equipment probably in the space, and the buoyancy can play an important role. And as Bill pointed out, the displacement ventilation works on that principle. Rate of contaminant generation, of course, how many people are there, how many are contaminated, where they are sitting. So location of contaminant generation. And finally, the layout of the facility. These are the obstructions to airflow, the furniture, the cubicle walls, and whatnot. So when we design the space, we design a space with a blank sheet on our drawing board. We rarely think, what is the height of the cubicles here? How people are sitting in the space can matter how air distributes. Now I'm going to tell you a few tales. And my first tale is the tale of 2 office spaces. This will be published in next month in National Journal. So in one space, 2 identical cubicles here, there are 6 people and there is 1 infected person here. And there is only 1 single 4-way diffuser, 1 single return, if at all it is there. In my observation, when I go and look for returns, I have to look for them. Where are those? Are there any returns? Sometimes those returns are in the corridor somewhere far from the occupied space. So there's 1 return, 1 supply here. In the other space, I have 2 supplies and 2 returns. I did not change the air change rate. This is 3 air changes in this space. Same amount of air is coming in both spaces. So if you look at the air distribution, what it says, when you are single diffuser, this air moves along the ceiling, strikes the wall, and creates a strong recirculation pattern in this cubicle. When you put these 2 identical supply diffusers, 2 returns, it creates its own loop of circulation. Not that it is free of circulation, but it is kind of creating a contained zone in each of these air supply and air return location here. Now, it has a significant effect on the on how you clean the space. Now, Bill talked about Wells-Rayleigh correlation, and I used it in this computational fluid dynamics analysis. And you can see, without increasing the airflow rate, how you place, how you bring the air where you place your return plays an important role. And you can see this makes a significant difference on the probability of infection. This picture shows the probability of infection. Closer to the infected person, your probability is close to 100%. Once you go away from the person, your probability reduces. If you have a poor air distribution in the space and you're bringing all the MERV 13 best clean air into the space, poor air distribution can defeat all your strategies. In fact, the social distancing, you can see, you defeat the principle of social distancing by putting the poor air distribution into the space. And this very well shows that this is the animation showing a probable flow path of airborne pathogens. When you have one supply there and one return, if at all there, it kind of pulls all those germs everywhere into the space. When you have a path of least resistance for the germs to leave the space, contaminants to leave the space, they have no intention to cross over and get into another cubicle. If you draw a cloud of infection probability, this is like 10% or higher infection probability. When you have a single supply, single return, it almost covers 50% of the room and kind of swallows all the occupants in that bubble. If you don't increase the airflow rate, just distribute it properly and take the dirty air out properly, you can reduce it to 36%. Of course, when you have an active source of a contaminant, you can't bring it to zero or any reasonable low value unless you control the source, such as masks, wearing the mask, and checking people before they come into office and avoiding infected people to come. This another tale of two patient rooms. And in this patient room, we have one return generally in the entry door of the patient room. And these are some linear diffusers here. What I did is I moved this return to above the patient's head and made it 2x4 instead of just 2x2 or 1x1 foot exhaust there. And it makes tremendous difference. You can see these are the airflow patterns computed by computational fluid dynamics. You can see all this air is moving over the patient towards that return versus creating this colorful spaghetti in the other space. And what happens to the germs breathed out from the patient? You can see they spread all over the space, entire patient room. When you keep that small, tiny return there, and if you create a path of least resistance for the dirty air to leave, you can see the germs just get lifted and they find, here is my exit. Why should I go somewhere else? I can exit the room from there. This is the tale of two laboratories, exactly same lab, exactly same air changes. In one lab, I have 2 exhaust grills and 3 supply diffusers. Here, in other lab, I have 3 exhaust grills and same number of supply diffusers. It makes ton of a difference in the contaminant distribution. Same air change rate. Now, we can talk in terms of equivalent air change rate. Much higher air change rate you will need to get this kind of concentration. This is the concentration at the breathing zone, breathing plane at 4 feet height from the floor. And this animation also shows you the other aspects of air change rate. In fact, keeping the same air change rate, and if you create the path of least resistance for contaminant to leave, for same air change rate, you can deplete this room, clean this room much faster than the same room with 2 exhaust grills. And this is obvious how the the blue color is penetrating into the space. This is that same blob. It's a 25 ppm concentration. You can see this guy's face is completely immersed in that dirty cloud, which is occupying about 27% of the lab. Same air change rate. Throw one more exhaust grill, you can bring it down to 16%. And you will see how this red blob, a zone of high contaminant, moving into the space. And you will see that volume of that red blob on the right side is much smaller than the volume of that red blob on the right side. Exposure is the most important, not the absolute concentration, but the duration of exposure. If you multiply that that's the dose we are exposed to. And it is showing the difference between 2 and 3 exhaust bill. It is like your exposure rate also comes down, your dose also reduces, and for third person, it's a significant improvement. To summarize, I want to say airflow patterns determine the flow path of airborne contaminants. And that's why air distribution is crucial along with other mitigation strategies. We need to understand, this is a common sense, air takes the path of least resistance. However, that path of least resistance is not very intuitive. You can do some of the CFD analysis to understand that. Location and number of supply diffusers and exhaust bills matter. Just increasing the ventilation rate is not enough. I'm not saying don't increase the ventilation rate, but it is only part of the equation. The other thing is how you distribute that valuable resource. Form aerodynamic containment pattern of HVAC layout. As I said, try to increase the number of diffusers, increase the number of exhaust bills, arrange them in a symmetric fashion, covering different zones so that you can create the aerodynamic airflow patterns, which will not promote the cross-contamination between the zones. And they understand the airflow patterns in a space. So that's my message. These are my publications. You can Google them. In your handouts, you will have those. I would like to thank my company for giving me this opportunity and funding this research. And I think that concludes my talk.
Thank you very much, Dr. Kishore. It's always very, very interesting listening and watching your presentation, because the way you make it so easy to understand, though it's not so easy to implement for sure, because it does need proper science to design air distribution, which is unfortunately ignored. But you make it so easy to understand the importance of the correct air distribution. And this myth of, I won't say myth, we're talking about pumping in outdoor air, also to positively pressurize a room or an occupied zone. And we believe pressurization in a layman's language, or even an HVAC engineer's language, means you open the door and you have a blast of cold air hitting you. And we really do not understand the big negatives of handling that kind of a situation. So it's very interesting, and we will come back to you for a few questions later on after the next two presentations. Thank you very much. Thank you. I would now like to invite Dr. Stephanie to come on the platform. Dr. Stephanie Taylor needs no introduction. She's been one of the most visible faces last few years, especially the last year and a half in this aspect. An MD from Harvard Medical School and a MArch from Norwich University, a very, very unlikely combination. I have never heard this combination. A practicing physician and a cellular biologist for several decades, a member of the Mass General Brigham Hospital's Infection Prevention Steering Committee and Harvard Medical School Inside Health Fellowship. With ISHRAE, a distinguished lecturer, a member of the Epidemic Task Force, and a member of the Environmental Health Committee. Welcome, Dr. Stephanie. And I know you're going to be talking about two subjects on humidity control as well as continuous IAQ monitoring for occupant health. So over to you, please.
Thank you very much. And I am honored to be a part of this panel. And I also want to thank my colleagues from Building for Health for helping me get to this place in my knowledge and in our knowledge. So I always feel a little bit like a fish out of water as primarily a physician talking to engineers. However, we really are all on the same team. So the focus of my presentation is going to be on how we manage indoor air from the perspective and through the lens of human health. So in the next 10 minutes, I'd like to just touch on these three topics. One, the importance of indoor air quality, not just now during COVID-19, but moving forward. COVID-19 has clearly created tremendous challenges in keeping us healthy and keeping lots of aspects of our lives moving forward. But I am grateful, and I will use that word, for COVID-19 in clearly illuminating the value and the importance of the indoor environment to protect human health. So instead of limping forward for 50 years, trying to decide whether this is important, we all now very clearly know that the indoor environment is key to protecting our health. Then I'd like to talk about how we actually bridge our gap, our knowledge gap and our functional gap between HVAC settings, building management, and human health. And thirdly, how do we manage the indoor environment? How do we scale this approach for building occupants all over the world? So right now, we have come together around this very agile, rapidly mutating coronavirus, the SARS-CoV-2. It's agile in that it mutates rapidly, it adapts to new environments, it finds new hosts, and it travels through the air, like most virulent viruses. However, once we are past thinking about this as much as we do now, the CDC reminds us that, we still have to consider other viruses and bacteria that are mutating to create disease. Having talked about infection control and infectious diseases, it's also key to realize that the indoor air quality is not just around preventing infection. So while we might have scared ourselves into being aware of how important indoor air management is for disease, we also have to remember that we spend most of our time indoors. I live in a beautiful state. I love to do things outside, but I'm still indoors about 90% of the time. And if you think about how much air we exchange with our body fluids and our body tissues, this number, we inhale about 11,000 liters of air every day. We also know that things that we really were less aware of that are key to preventing disease transmission, things like relative humidity and a mid-range relative humidity, which inactivates many viruses very quickly. A study in 2007 showed that 80% of influenza A virus is inactivated in 15 minutes when the indoor ambient relative humidity reaches 40%. That's a very key statement. We also know a lot through Dr. Joe Allen's work that when carbon dioxide levels rise and other indoor pollutants, our productivity and our cognitive functioning diminishes. So having highlighted this relationship between the indoor air and human health, we definitely need to expand our definition of a healthy building. It's no longer just a green building that protects the outdoor environment and diminishes outdoor pollution. We now need to address the indoor environment, as my colleagues have already discussed, but we need to expand our metrics and our definition and our standards. So while prior to COVID-19, after the oil embargo of the 1970s and LEED, we've really focused on carbon fuel consumption. ISHRAE talks a lot about comfortable occupants. We clearly want our buildings to have a high real estate value. But now, with this increased perspective, which includes human health, we need to also consider these other metrics. We need to minimize infections and inflammatory disorders that are related to the indoor environment. You may or may not know that cardiovascular disease and even diabetes and obesity are related to the exposure of particulate matter, a lot of which comes from the indoor environment. We need to control these things to keep all of us healthy. We need to minimize VOCs, off-gassing. We need to minimize the interaction of VOC and things like ozone to prevent hydroxylation of gases, which create a bigger risk for oxidizing human tissues. We need to optimize thermal conditions, so temperature, relative humidity, to support our physiological functioning and to, surprisingly, decrease the virulence of many viruses and bacteria. So we need to expand our definition. This is not, we can expand the definition, but actually doing it is challenging. And it's challenging because if you just look at this chart, and I'm not going to go through each row or column, but clearly, if you look at buildings and indoor air quality evaluation on the left, we have different tools, different language, and different metrics for evaluating buildings and indoor air quality when you compare those, that whole world to the world of medicine and health. So while with air quality evaluation, we can look at viral and bacterial counts, in medicine, we look at infection rates. And again, I'm not going to go through each row, but you can see the words are different. So how do we do this? How do we combine these two silos? Well, a great place to look at the relationship between human health and the indoor environment is actually in a hospital. So this study, which if you've heard me speak before, you've probably seen several times, is from 2015. It was done in a brand new hospital in the Chicago area, beautiful LEED Silver Hospital, brand new. So microbiologists were mapping the movement of organisms through this space. And I found out about this project, and I wanted to look at patient outcomes. So if you think about a hospital and you think about the patient data, I want you to view the patient not now as someone you care about or yourself. I want you to view the patient as like the petri dish in the bed or the biomarker for the patient room. So that was the approach in this study, where we monitored for 13 months, gathering environmental data every 5 to 30 minutes, all of the things you see listed in the middle. Again, brand new hospital, all private rooms with vestibules, private baths. So we looked at the 11 things you see listed in the middle: temperature, hand hygiene compliance, pressurization, lighting, CO2, humidity, traffic, room air changes, and outdoor air. So we had about 8 million data points from the physical environment. We correlated those data with patient outcomes, and specifically with new infections that people are exposed to from the hospital environment, called healthcare associated infections. So we had a massive amount of data, which we sent to our statistician. And so, I thought we would probably see that hand hygiene compliance would be the top of the list for correlation with infections, or perhaps, room traffic. However, to my great surprise, and I think to everyone's surprise, our statisticians came back saying that of all of the both steady metrics and the monitored metrics, which were varying, that the most powerful correlation with a higher infection rate was low relative humidity, and not absolute humidity for all the engineers who like the psychrometric chart, but low relative humidity in the patient room. So clearly, if you look at the x-axis, when the indoor relative humidity was less than 40%, you see on the y-axis that the average number of infections, particularly respiratory and gastrointestinal, both viral and bacterial, were higher. And when the indoor relative humidity reached 40%, the infection rate was at an all-time low, and it stayed low, began to go back up again around 60%. If you're looking at the dotted green line, those are urinary tract infections, which tended to follow other more behavioral things such as mobility and hygiene. However, you can see with cellulitis or skin infections and eye infections, they still trended down. So this was absolutely fascinating. We didn't believe it at first. We've got a new statistician who confirmed that this is an independent variable, separate from any of the other confounding variables. So again, relative humidity, 40 to 60% is good for people. And if you look at the interaction of indoor water vapor with our other systems, not just infections, if you're sitting in a room with around 20% relative humidity for 8 hours, even if you're not exercising, unless you have an IV drip continually rehydrating your intravascular compartment, even if you're sipping water, you're going to be about 1.5% dehydrated in less than 8 hours. So this mild degree of dehydration affects our eyes, impairs our vision, skin inflammation increases with the associated disorders, and wound healing is decreased. We know that our brain function is diminished. People become fatigued around 2 in the afternoon. And yes, you can drink coffee, which I do, but it's not only the caffeine that's probably helping you, but the fluid as well. Hand-eye coordination is diminished when you're just slightly dehydrated. And we also know, and this is very relevant for this time, when the relative humidity is low, your respiratory system does not protect, your respiratory immune system does not protect you as well. The great study by Akiko Iwasaki at Yale, 2019, in the PNAS, Proceedings of National Academy of Science, which really sheds light on what happens to our respiratory immunity in low humidity. Another thing that we've learned by looking at the indoor environment through this lens of human health is that our whole previous conception of hygiene in the air, hygiene on surfaces, and our previous idea about our bodies has been really wrong. We used to think, using tissue culture techniques, that germs were bad. If you were sick, you identified a bacteria, for example, in your throat, you took an antibiotic and you tried to eradicate that germ and many others. We now know that those visualization techniques of tissue culture only revealed a very small number of all of the bacteria and viruses in our bodies, on our bodies, and in our buildings. So in fact, all organisms are not bad. Each of us, by cell number, is 70% bacteria. So each of us is like a little ecosystem enclosed, walking around, shedding our organisms and interacting with the building. We now know that, in fact, we need microbes. We need good microbes to be healthy. We need microbes to digest our food, to train our immune system, to prevent us from having severe neurological disorders. And in fact, if you attempt to kill all bacteria and viruses in your space or in your body, you're going to eradicate the good ones, the commensal organisms, which then makes way for the more virulent pathogenic viruses and bacteria. So while it's fine to try to eradicate everything if you're in a bone marrow transplant unit or a burn unit for a short amount of time, but we need to move away from this idea that all bacteria and viruses and fungal organisms are bad. That's not true. And in fact, studies in Amish cultures have shown that children and people who live with animals who are actually exposed to soil organisms, and dogs in particular, actually have a more robust immune system. So unless you have a specific allergy to dogs, they help you in many, many ways. And one of the ways is they expand your microbiome. So you don't want your operating room to look like that bed, but it's fine to be rolling around with and interacting with these broader species of bacteria. We also know, by looking at the indoor environment through this lens of human health, that we can measure particles and gases and pathogen levels individually, but we know that, in fact, it's the interaction of these things that are very impactful to our health. This is a modified image from Ma et al. 2020. It shows that it's really the interaction of particulate matter, different gases, sulfur dioxide, nitrous dioxide, ozone, and other things, pathogens, and humidity that impact our respiratory system in very synergistic ways. So if you look at this graphic, again, it shows you how that works. And it's the interaction of these things that has both acute and chronic effects on our health. So when we think about evaluating the indoor environment, we need to, again, keep in mind that it's the health impact that we're really concerned about. So how do we take this very, for example, a labor-intensive process such as the hospital study in Chicago? How do we scale that so that all occupied buildings around the world can be evaluated from this key perspective of human health? So this is where I've been working hard on this with my colleagues at Building for Health. And what we are doing now is, through automation and through our software platform and sensors, we're measuring in a continuous fashion the indoor metrics that we know are related to human health. We gather those frequently, we run them through a health algorithm, and that algorithm is actually, it's 2 words and a little blue arrow, but it's actually the result of decades of medical research. It's the result of looking at death and disability associated lifetime years, animal toxicity studies, cellular biology studies. And by combining those metrics that you see on the left through our algorithm, we come up with a health impact rating for the indoor environment, which is then actionable. You can modify the underlying components of your indoor environment that create the health impact, so that if your rating is low, you can improve it. So again, I'm trying to keep within my 10 minutes. We can have lots of discussion about this in the upcoming panel. But if you don't measure the health impact, if you don't, whatever it is, if you don't measure it, you really can't manage it. So while pathogen infectivity and host defenses are two areas of the indoor environment, the health quality of your air, surfaces, and the mixture of those will create a healthy or an unhealthy environment, which, as you can see by the red area, really changes dramatically your chance of disease or health. So it's really exciting as a physician who's trained in architecture, and I work a lot with ISHRAE, bringing the medical lens, a health lens, to managing the indoor environment. And when COVID-19 is just a bad memory, we still need to remember how important managing our environment is for our health. So I say thank you to ISHRAE, and thank you for including me in this panel. And thank you to my engineering colleagues in B4H. And this was a couple of years ago when I was in New Delhi with my esteemed engineering colleagues. So thank you very much.
Thank you very much, Dr. Stephanie. A very unique take on how to view indoor air quality. And unfortunately, we never looked at occupant health as a very important way of designing HVAC. It always used to be more about temperature and humidity and comfort inside. And the health aspect was largely ignored in most applications. And it's something which now needs to be addressed very properly by the HVAC design community, the engineering community. And you cannot ignore it. COVID today, and it could be something else tomorrow, or in general for life ahead. So thank you very much. Thank you very much for sharing your thoughts on it. We will come back to you with some questions at the end of the next panelist, and look forward to some more queries over there. So thank you again, Dr. Stephanie. I would now like to invite our very own Mr. Gautam Baliga. He's the last speaker on the panel, after which we will have the question and answer discussions. Gautam is a BTech from IIT Kharagpur, a director at Opal HVAC Engineers Private Limited, Mumbai, also a partner with RS Kulkarni HVACR Consulting Engineers. At ISHRAE, he is the chair of the Healthcare Technical Group. He is a member of the COVID Task Force, and he's a member of the editorial board of the journal. He's also a member of CII, IGBC's task force to write the green guidelines for fast track and emergency facilities for treating COVID-19 patients. In ISHRAE, anything to do with healthcare and HVAC, he is the person to go back to, and he's the best person to share his inputs with us today on this subject of healthcare for fast track and emergency facilities. Over to you, Gautam.
Thank you. Can you see my screen?
Yes, Gautam, very clear.
Okay. Ladies and thank you, Vishal. Ladies and gentlemen, a very good evening to you. I feel quite honored to be speaking in this forum. I'm going to talk about HVAC for fast track and emergency facilities for treating COVID-19 patients in India. India being a developing country with a population of 1.3 billion, the government is taking various initiatives to address the challenge posed by the pandemic. In this presentation, we'll talk about the facility types as per resources available. Then I will talk about parameters to follow to ensure containment of contamination and recommendations as per resources available. Vishal touched on this. ISHRAE launched two important documents. One was a general document and the other was focused towards healthcare during the last year on COVID-19. And what we did for the fast track facilities has taken a lot of inspiration from these two documents. COVID hospitals are either greenfield projects or are converted hospitals requiring a different approach to HVAC. IGBC, that is the Indian Green Building Council, developed green guidelines for fast track and emergency facilities for treating COVID-19 patients in August 2020. It has been adopted by Niti Aayog and issued to all the COVID centers in metros and all district centers in India to follow. Niti Aayog is a government body, and I had the privilege of being part of the task force for the HVAC part, which was obviously considered to be crucial to contamination control. The 3 levels of the hospitals are like this. Level 1 is for the symptomatic COVID patients who require only quarantine facility for mild illness. The level 2 COVID hospital is where they provide oxygen for those needing the same, but they do not have intensive care facility. And lastly, you've got the level 3, where ICUs and oxygen and mechanical ventilators are also available for the patients. Sorry, there is a broadband issue. The infection control strategies in HVAC. These are the strategies. You've got the pressure relationships of areas and airflow currents, which determine where the contaminated air is moving. Then we have got the air change rates of fresh air and recirculation to determine the dilution of pathogens. Handling the exhausts, especially from ICUs, isolation rooms, and connected toilets, and appropriate filtration area-wise. Temperature and humidity. Temperature is integral to comfort, and you need to be mindful where the healthcare workers are wearing the PPEs, which will require lower temperature. RH levels are also addressed. And finally, use of UVGI is advised in various formats for air purification. We have advocated 4 types of HVAC systems. You can see first is the AHU systems with filtration and adhering to ISHRAE standard 170. Then we have various combinations of unitary equipment with wall units, window AC units, cassette units. Then we have got the mechanical ventilation systems for supply and exhaust. And the 4th is the natural ventilation system. Needless to say, the natural ventilation is the cheapest, followed by mechanical ventilation, then unitary equipment, and the costliest is the HVAC systems with AHUs. Now, which option to adopt for air conditioning? With AHUs, we provide necessary filtration, induct fresh air, and provide dehumidification, create pressure gradients. This is the proper option for critical areas like isolation rooms and ICUs, and the preferred option for quarantine and triage. Good option for all other areas in the facility, but then you have to evaluate the economy. Unitary equipment like wall units and window units and cassette units are economic options, can be considered when mechanical ventilation can't be giving comfort. These units can be used in quarantine, triage, patient waiting areas, doctors and nurses' rooms. Downside is that there is no filtration or fresh air. Providing for separate fresh air and exhaust is a must. Then coming to the ventilation systems, which is the right option? Mechanical ventilation systems. It is an option where the climate is favorable. It is accepted in areas like quarantine and triage, areas like resident gathering, activity, dining, physical therapy rooms, wash, janitor rooms, storerooms. Can be used when there is no risk of heat stress or pollution due to ambient air. Can be used when natural ventilation is not practical. Then we have got the option of natural ventilation, which depends on favorable climate conditions There is no risk of heat stress or no air pollution, can be considered instead of mechanical ventilation when the room location and building orientation make natural ventilation feasible. The downside is that it is subject to changing climate and wind velocities, and most important, it needs very careful engineering design. Pressure gradient in hospitals. This is a diagram out of the green guidelines of IGBC, and it shows the various areas, the staff areas at higher pressure, the waiting area, triage and all at lower pressures, the laundry and services area at positive pressures so that the workers don't get into any danger, and all the various other areas are under various pressure gradients. You can see that on the left, you've got the yellow, and those are for the short stay patients, basically for quarantine, and they have got a particular pressure. And then you've got on the top, the level 2, the severe cases at more negative pressure. And then similarly, the level 3, the critical care patients, which are at a very low pressure. The main idea is that the pressure gradient is at the heart of the infection containment strategy in HVAC systems. Exhaust systems for isolation and ICU are on emergency power to ensure negative pressure at all times. Now coming to airflow patterns, I'm stealing a page out of Dr. Kankari's lecture. It's a airflow pattern that really counts. You can see on the left, that is the airflow pattern for the ICU. The supply air comes directly to the healthcare workers and then moves on towards the patients, and then, all with their respiratory exhausts, it goes into the return air or the exhaust. In the case of negative isolation room, you can again see that the clean air comes directly over the healthcare worker, then moves on to the patient, and then all that respiration goes directly into the local exhaust. Air distribution is to ensure that the virus-laden air is quickly replaced in the zone with clean air. The virus-laden air is led away out of the harm's way by positioning the exhausts appropriately. Then we talk a little more of the air distribution. Air distribution in the room should avoid turbulence, which can result in contamination spreading uncontrolled all over the place. The placement of grills and diffusers and the sizing should be such that there are no air drafts. Typically at occupancy level, air velocity should be low and near 0.2 meters per second. And fabric ducts is considered an option. Fabric ducts can be used for supply as well as exhaust or return air. These ducts are now available with antimicrobial and fire rating. Number of air diffusion options are available: linear vents, nozzles, orifices, porous fabrics are available. Air purification, this is also being recommended in the facilities. UVGI and AHUs for cooling coils and condensate drain pans, duct-mounted UVGI for recirculatory AHUs-based systems to kill virus and pathogen in the supply air, and upper room UVGI to work in conjunction with unitary AC units, mechanical ventilation systems, and natural ventilation systems. Modes of contamination exhaust. We all know that we have got a pressure gradient, and all the contaminated air goes towards the negative pressure, the deep negative pressure regions, and at some point of time you have to exhaust that air. And how do you exhaust that air is very important because it is highly contaminated air. First option is through HEPA. You pass the exhaust through the HEPA and then into the outside atmosphere. The other option is to disperse it high up, about 3 meters above the vicinity building or the building itself, and disperse it into the atmosphere. The third option is the chemical treatment, and this is using, you can see this particular diagram, chemical disinfection of the exhaust air by bubbling it through diffused air aerator tank holding 1% sodium hypochlorite solution. Why this is considered a very important recommendation is that in the most distant hospitals in India, you'll find that sodium hypochlorite is available in every hospital, and that is why this is a recommendation. And the only downside is that someone has to keep an eye on the water levels, and that the sodium hypochlorite solution is being maintained at the 1% solution level. Then we have got a menu list for each and every room inside the facility. Just to give an example, you've got this ICU, and we talk here of what should be the temperature, what should be the humidity, room pressure, minimum fresh air changes, whether recirculation air is allowed. And coming to the type of equipment, here we say that only AHU is allowed, but then unitary AC plus fresh air modules is allowed only for converted hospital facilities. Mechanical ventilation and natural ventilation is not acceptable. Then coming to filtration, MERV 7 plus MERV 14 is the minimum we expect for the AHU. Then coming to the fresh air module of the unitary AC, we expect MERV 7 plus MERV 14. Mechanical and natural ventilation, of course, is not the option. And we talked about the 3 modes of exhaust for the exhaust air: H14 HEPA or chemical treatment, or plume for exhaust for both AHU as well as unitary systems. And the recommendation is for UVGI for cooling coil for AHU option. Similarly, for the quarantine, you'll see that you've got the temperature, relative humidity, and fresh air, minimum recirculation is given. In this particular case, you'll see that AHU is an option. Then you can use unitary AC plus fresh air modules, or you can go for mechanical ventilation system, or you can go for natural ventilation system. And then on the filtration side, there is a menu card out there. You go for the MERV 7 plus MERV 14, or you can, along with the unitary AC, you go for the fresh air module with MERV 7 and MERV 14. And for mechanical filtration, you go for MERV 7 and MERV 14. Natural ventilation, of course, you can't expect to do any filtration. All exhausts in this particular case, because the viral load is considered much less, it has to be, you have to be mindful where you exhaust that air, and it has to be in a safe place. And you'll see that in all the area, in the quarantine areas, we encourage the use of upper room UVGI recommended for all the options, UVGI for cooling coil for AHU option, duct mounted UVGI for the supplier option. So likewise, this has been stated for each and every room in the facility. And to summarize, the document recognizes that there could be several options of HVAC for various areas. The option to select has to be based on the realities of the location and what is practical for that particular location. Thank you. Vishal, that's it.
Thank you very much, Gautam, for taking up a very important aspect of COVID, because the healthcare team, the healthcare infrastructure, the healthcare resources have been the hardest hit over the last year plus, and we salute all of them down in the field for taking it on. And it's very important to upgrade the existing infrastructures as well as a lot of new facilities being put up, some following protocols, some not following protocols, and not following protocols is much more dangerous because what it does to the other patients and healthcare workers could be disastrous. So thank you very much for sharing these findings and recommendations in a concise manner. We now come to one more interesting part of the event, where I would request all our panelists to put the videos on and be visible on the screen out there. Thank you very much. We realize that we're going a little overboard on time, but I think the audience is loving it, and the responses we are getting is phenomenal. I know a lot of questions have already been replied by a few of you directly to the panelists on the question box. I'm going to limit my questions to some very interesting ones, some which are going to be a little bit more specific to India or developing countries, and could also be specific applicable other places. I'm going to start with Dr. Bantlet. Well, we talked about increasing outdoor air ventilation, increasing outdoor air changes, specifically to outdoor air. I'm not talking about the air cleaning aspect after that to get equivalent air changes, but the outdoor air changes. Now, we stay in a country which has huge amount of outdoor air pollution. We also have very extreme climate conditions, both on temperature or humidity point of view outside. A question being asked to us is that you're asking us to increase ventilation, but what about the other problems that would come with it? How do we take care and what do we advise in that?
Sure. And of course, my answer to that would be that I didn't really say you should do that. I was talking about ventilation, and if you had an uncontaminated, from the point of view of viruses, supply of air, how much would it take to reduce the concentration to one that achieved acceptable risk? I also mentioned, though, that that's probably not the best way to do it, even in places where the outdoor air is of good quality, because of the energy impact and the potential for not being able to maintain indoor temperature and humidity conditions. So I agree that you could probably make indoor air quality worse overall by going to 100% outdoor air in many places in the world. Delhi on a bad day, Beijing, because of the PM levels and possibly ozone and other urban contaminants. So I think you have to really understand these recommendations about ventilation in terms of uncontaminated air changes. And if you're in a place where outdoor air is an undesirable way to deal with infection risk, then look to filtration and air cleaners and more efficient air distribution as ways to do it.
Oh, thank you. Just an add-on to that is, with all these modern buildings, nowadays architects talk of modern buildings. This is an open question to anyone, and which are basically glass boxes, and they just love those kind of building designs. How do we handle in case over there and we need to get in air from outside? What is our clear advice to building designers in this perspective?
I could
Anyone?
take a shot at that.
Yeah, Gautam.
See, there is a demand for glass facades to make buildings more prestigious. You can't wish it away. These are energy guzzlers, everyone knows that. But fortunately in India, most such buildings have glass facades outside, but then there is a separation and then the main wall. The HVAC engineers will have to use their ingenuity to source the fresh air from this gap and then exhaust the air through the shafts. That's the way we do it. But then there is good news that there is pressure on these buildings too to become green and net zero, hopefully. There are already buildings coming up, of course not in India, where entire gap between the facade and the main wall is being used as exhaust by siphoning of air and keeping it cool so you can get the summer heat out. So as I said, that is in the future, but you can never know. Before long, it will be there in India. Thank you.
Thanks, Gautam, for clarifying that. Dr. Kishore, we heard from you the importance of air distribution, the importance of picking up air, whether it's for return recirculation or for exhaust out. Now, a lot of public spaces in these countries, including our country, does not have ducted systems. They thrive on wall-mounted units or ceiling-suspended cassette kind of units, where you really cannot do much of change in the way of air distribution. But these are public spaces, whether they are restaurants, whether they are schools, they could be showrooms, offices, and all other kind of applications. Now, how do we take care of air distribution or air flow in this kind of an application?
Well, it's a difficult question, really, Vishal. I mean, if you say that everything is set in stone and then give me the clean air, well, either we learn to live with it or find a way out of it, correct? I mean, whole premise of my presentation is based on airflow patterns are not given, they're created. And a good engineer can understand the physics of air motion and very low hanging fruit is air takes the path of least resistance. I mean, and though it may not be intuitive, but at least we can stretch our mind to think about it. And we need to at least move something here and there and try to understand. One common sense is like, don't try to exhaust the air over the occupants. Okay? I mean, if you have a restaurant and seating place, please don't put all the sweep contaminated air over the occupants and then take it out. Okay? Sweep it away from the occupants. So if you have any opportunity or any leeway to move few things around here and there, that will help. Then come to Marva's thing. If you cannot do it by the AHU part of it, then have the local controls like indoor air cleaners. Now, where to place them? At least that is in our hands. I mean, it is not just you buy an air cleaner and put it in a room. As I said, it's not guaranteed to create a clean breathing zone for you, because where that air is sucked out and where it is clean air is supplied should work in harmony with the airflow patterns in the room. Okay, so I have seen air cleaners put people they are putting on the floor, and they are taking the air near the floor, taking it out near the floor. I said, well, is this a vacuum cleaner or air cleaner? What is it? So we have to stretch our imagination a little bit just to think what best we can do.
As you said, and Marva also touched upon air cleaning and portable air cleaners or fixed type of air cleaners inside the rooms. And we talked of various active technologies, electronic technologies that have come across. Now, a question comes that the risk of COVID or the risk of fatality out of COVID is huge, right? And we've seen the deaths and the cases all across. Now, how much risk should the industry take when you have new technologies coming your way, which have not necessarily been researched or proven till now, but have some kind of impact or not, and vis-a-vis the fatality rate of this virus and the risk? So, what kind of a risk can one take, or should one not get into a proven technical until it's proven at all? So, where do we balance this whole equation of a risk due to COVID or the risk due to a technology which is yet not proven?
I can start a little bit about this. And this is not unique only for these emerging technologies. We've seen two specific trends. So the first trend to say that it's better than nothing. And the other one, like basically, if it doesn't do if it doesn't do good, it's not going to do harm. And the problem here is that you have a limited budget always. So any dollar you spend or the currency you spend on unproven technology, you're taking it away from proven technology that can actually reduce the risk. The other thing is that you might have a false sense of security. Like we've seen the rise of plexiglass. So these two notions are important, and they can mislead of what actually need to be done. Dr. Baumfleth talked in general about the airborne dilemma. So it's very important to say it, is that these are proven and we know how much risk they can reduce, and this is how much is the dollar per risk reduction. I know like when we talk about dollar or energy, it just seems like a little bit bad, but the reality is that everything happened on a budget. So it's important to talk about the dollar per risk reduction and what we understand. So thankfully, we have technologies. We talk about HEPA filtration. Maybe the outside air will not be as useful in India and other part of the world, but you have air cleaning technology that are proven, like MERV and HEPA, UVGI, and you can use a combination. Why not go there instead of venture in unproven technologies? And the problem is that when COVID finishes, and hopefully very soon, you're going to be stuck with these technology that might be harmful in the long term. Specifically, I'm concerned about like schools, where our kids will be subjected to these technologies every hour of the day throughout their whole school year. So they're not going to turn them off, right? They're going to still be there. And maybe we're not going to think about indoor air like we're thinking today. So what happened during COVID also sets the stage for how we take care of indoor air quality in our buildings.
Oh, thank you. Thank you very much. A question to Dr. Stephanie. Yeah, please.
Yeah,
Please.
thank you, Vishal. I want to supplement what Dr. Marva is saying. I think innovation is heart of our human beings' progress and well-being and our establishment. So we should always encourage innovation, new thinking, new thoughts, new technology. However, we have to keep the commercial part separate from the physics part or science part of it. And there is a huge burden on organizations like ISHRAE and ASHRAE to look at this in a third lens, in an independent manner, taking help of world experts on this, and do this in an impartial way to tell people the good and bad part of each technology. I think we should not kill the innovation. Sorry, go ahead, Doctor.
No, I interrupted you, Kishore. So I just want to second that. From my perspective, that creating this visibility into the indoor environment through monitoring will help us determine when you need an intervention. Some buildings are going to be fine, and we can't always tell. It's not always the shiny stainless steel and glass buildings that are the best. But by monitoring the important variables, we can tell when do you need an intervention. And when you do implement a strategy, whether it's filtration or increased ventilation or an air cleaning technology, is it achieving the results that you hope to achieve? So I think that monitoring, and again, to respond to what Kishore just said, that technology is absolutely key moving forward to seeing what the indoor environment is doing for human health.
That's interesting. So, and when you talk about monitoring, like if I go to the humidity part of it, now bulk of the comfort applications, as we see in India and bulk of other countries, they do not control the air conditioning operations as a perspective of humidity. They just control it from the temperature perspective, whether it's a plant of a chilled water or a direct expansion plant. All that we're doing is we're controlling it by the temperature, and most cases, if not all, there is no control linked to humidity. Whereas you have very correctly spelled out the importance of control, keeping the humidity in that slab of 40 to 60 odd percentage. Now, how do we do that when there aren't any controls to, you can, even if you monitor, but beyond that, you're not able to control your air conditioning performance to get that humidity level. So what do we do for such huge amount of comfort applications out there?
Yeah, so that's a great question. What happens when you cannot achieve that 40 to 60%? What happens when there's not a response to a hygrometer that lets you easily do that? And you're bringing up the condition in India, which is high humidity. In many countries that have cold winters, we struggle with low humidity. And you're right, some buildings cannot achieve 40 to 60%, try as they might. But the beauty of monitoring is that if you can't achieve that humidity range, it will also recommend other interventions that supplement your indoor air management to bring it into a healthy impact rating score. So it's not just one technology necessarily, it's the interaction of different technologies and different indoor conditions that is going to result in a good indoor environment. So I see what you're saying, and I wish we lived in a perfect world where we could just, snap our fingers and have the conditions we want, but clearly that's unrealistic. So it's just another reason to monitor, in my opinion.
I get the point. And when we look at the current installations, I just go back to Dr. Kishore or anyone else who wants to handle it, whoever. A lot of our designers today, architects, interior designers, love to design open ceiling, open office layout. That's the new fad. No return ducts, no false ceiling, round ducts, square ducts, various kind of ducts going all over visible. There's no return air plenum also for false ceiling or return air duct. And when we look at your presentation, whether here, the entire air of our air handling unit of 6,000, 10,000 CFM is going all in one direction of the HU. Now, what would you like to say on this forum to such designers and HVAC engineers to how do we handle such jobs?
What was the last part of your question? I didn't understand your last sentence.
How do we handle such cases, where we are being asked to design more and more of open ceiling layouts? No return ceiling plenums, no return ducts. Is that a good design perspective? Okay, let's go from that. Is that a good design?
Let's monitor and find out. Every building is going to be different. And other than that, I'm going to turn that over to someone else, like perhaps Kishore.
Oh, okay. Again, I go back to the same thing I said, innovation, new ideas, new ways of living and making ourselves comfortable. No idea is a bad idea, correct? Unless you prove it. And the burden again on us to prove whether this open ceiling is a good idea. Again, top of my head, open ceiling means you have higher height. Then why can't we use some of the stratified strategies so that you can make good use of the heat, the sensible heat in the occupied spaces, and use displacement or static or UFAD kind of situations. Not having any return in any space is, for me, very hard to imagine. I mean, may not be a return called return, but that air is going somewhere. Correct? I mean, there may be open door, open corridor. Now the question is that the path of least resistance for the contaminants to leave the space? Are we taking those from one space and putting it into other space? So again, there are pros and cons of each idea, and it has to be tested and improved.
There's been a lot of discussion recently that seems to make more of the importance of returns than traditionally was the case. I was always taught that it was supply jets that really determined where the air went, and that the return could be for just about anywhere. Of course, that's mixing ventilation, but perhaps we need to have better guidelines for how returns are laid out. What is enough? We think a lot about diffuser patterns in large spaces, a little more attention to returns, and maybe that problem is solved. I have a 15-foot ceiling in my office. I don't worry too much about the airflow patterns in the breathing zone, with the return being way up there and only having one of them. To your point, Kishore.
It is naturally displaced.
I wanted to say one other thing about the previous discussion was we believe in innovation, but too many people believe in magic, and that's the problem. When you tell them the solution is more ventilation or a better filter, they say, "Really, that's all? Don't I need some special thing?" And that's been a big part of, I think, some of the problems that we've had in the last year.
And a lot of people have been asking questions in the panel over here, otherwise also about UVGI. Dr. Marva covered it briefly in her presentation. No one better than you to extend further from what she said. There are proven technology. UVGI is a proven technology, but the way that's being applied at times is not necessarily the right way, whether it's in HU, in duct, or the way it's being put up room. So if you could throw a little bit more light in a brief manner as to what is the right way of some, I won't say tips, but some of the right ways of handling UVGI. And for what purpose? Disinfection or surface disinfection, air disinfection?
Well, right now we're not that concerned about surface disinfection, and with 254 nanometer being the standard wavelength, and until we get far UV that might be safe to use in occupied spaces, then surface disinfection has to be done when occupants aren't present because of the risk of skin and eye irritation. In terms of overall effectiveness, putting an upper air system into a space is going to be the most effective. Those have been tested out at 50 air changes per hour equivalent or higher. It depends on the intensity and also on the pathogen that's being treated. If you put it in an air handling unit, the largest clean air delivery you're going to get is whatever the supply air flow rate is of that system. So if it's a VAV system, maybe 6 or 7 air changes per hour, but you're also putting the UV in series with the filter. So if you have a high efficiency filter already, say if you had a MERV 13 filter and you put a 90% efficient single pass UV system in series with it, it might get you another 25% above what the filter's doing. So there's a trade-off there that the designer has to be aware of. But the other thing I'd say is that coil maintenance is really a good thing, and that having UV and air handling units to keep the coils clean is a side benefit of doing it that way. The other thing I'd say is that in terms of cost per unit of space protected, central air handling unit installations are going to be considerably less than doing a whole building with upper room. And I think the upper room is just not feasible for most places because of the cost, but you can have a reasonable addition to the level of protection by putting it into an air handling unit.
And I'm gonna talk a little bit. If you see a UV system in a portable air cleaner that's used during occupied hours, be careful. Because we've been seeing like marketing that mix a proven technology, like UVGI, like Dr. Banfles talked about, and then UV-PCO. So UV used in a photocatalytic oxidation system is completely different. So, and I've been like victim of that, and I had to return the things that I bought. So if you have a portable air purifier with the UV-PCO, this is not the same as UVGI, and it's not proven not to be effective, not to be safe. Now, there are some instances where they put a HEPA filter and a UV light to shine on it. That's not useful, but separate. So if you see a UV plus a catalyst, usually titanium dioxide, this is not proven and not the same as UVGI.
So one big question that I have about germicidal technology such as UVGI is how do we reconcile the use of UVGI, for example, in an overall space with the concept that we don't want to kill all organisms? And I'm almost reluctant to bring this up in a time when we're worried about a very virulent virus. But we do know that the microbiome of the built environment interacts with our microbiome. And just like we don't want to take antibiotics all the time, we need to allow the good organisms to persist in most spaces, not in an operating room or bone marrow transplant. But other than using, for example, UVGI in a ducted system where you're keeping the different components clean, I have questions about the overall germicidal approach to occupied spaces. And I was just wondering, Bill, you and I have probably interfaced on this before. I don't remember exactly, but what are your thoughts about maintaining a healthy microbiome in the face of germicidal technologies?
Yeah, it's an emerging field, and until we can somehow sort out the good germs and the bad germs, we kind of have to take the old kill them all and let God sort them out approach. But that's the same thing as if I clean a countertop with a disinfectant. I'm doing the same thing there. So, but I think that the goal is not to sterilize spaces. That's maybe the first point, is that we're trying to reduce levels of certain things to what we consider to be levels that pose a reasonable amount of risk, and you're not sterilizing your environment by having UV in the air handling system. There are all the surfaces in the building that it's not treating. So I think it's a concern, but there's no good way of dealing with it yet, and no UV system that I know of, except the ones that are used to sterilize test chambers that are doing biological testing, really has that as the goal.
It's interesting. I think it's a very interesting question. And thankfully, we do have some new tools, the metagenomic analysis tools, that allow us to see the result of the different technologies and how we skew the surviving organisms.
Very much like water, when we do water in reverse osmosis system of treating water, and now we have demineralized and then mineralized water. There are treatment plants which will first filter out everything else and then load minerals into the water, because while filtering out, you have removed even the good minerals. So something very similar is what you're talking about air. So yeah, I think that's something which is going to come up in the years ahead as to what to do and how do we handle in different shape. I think Dr. Kishore, you were wanting to add something.
I want to respond to Dr. Taylor's concern about killing good microbes. I think just placing I'm just talking about upper room, not the in-depth. A UVGI system in a space is not a guarantee of creating a clean space. That's one thing, because each microbe reacts to the UV in a different way. That is the susceptibility of that microbe. And there is a research required, an in-depth research for good microbes versus bad microbes. And all these good microbes are falling in the same bucket and bad microbes for their system. So I'm not the expert on that part of the how to expose and what is their, they call Z value of the microbes for the UVC exposure. The second part I want to bring it up that even airflow patterns play important role on the efficacy of UVGI. Try to understand you have a UV field in the upper part of the room, and these microbes and pathogens have to pass through that field, and they have to stay there for enough time to get inactivated. Of course, if you do the multiple pass, they are going to get exposed to several times. But airflow patterns also play important role. So UV intensity and how these intensities is exposed to the microbes and pathogens is the second part of this thing. So though induct may be very obvious, upper room UVGI is much more complicated in that sense.
Well, there's this concept of probiotic air that some people have talked about, and you can buy products, you can buy stuff you can put in your air to make it healthier. That probably falls right in line with some of the air cleaners we've been talking about in terms of its evidence basis. But you just a lot of the microbiome that keeps us healthy is on surfaces. It's on our skin. It's in our gut. And I would be interested to know how much our general health is affected by what might be in the air. I mean, the fun fact is we have more microbial cells on us than we have in our body. There are more microorganisms. If you added up everything that was in our gut and on our skin, there are more of them than there are cells of us. So it's with us all the time.
I think, in fact, the organisms in the air are very important for our health, and they've been shown to colonize our respiratory tract as well as deeper areas of our body that we never knew were colonized. And I think you have a microbiome diversifier walking on your desk right now. So cats are pretty good for that. Dogs are better. There's some interesting studies about the toxoplasmosis gondii antigen that's released from cats. It's associated with some different disorders, but I think we're going to find moving forward that the diversity of the indoor microbiome is absolutely key to managing the human microbiome, which we now know is related to, as I was saying in my presentation, neurological disorders, inflammatory and infectious disorders, a whole host of health consequences that we never realized before. I think it's going to be a really fascinating area that continues to emerge, but we can't ignore it.
No, not at all.
This thing on filters, and a lot of people talk that filters are primarily used for trapping the particulate matter or the virus or whatever else, but not for killing it. And there's a very, very critical word over killing the virus, a very, very dangerous word. But that's the way the industry is going, that this filter can trap and kill, this filter can only trap. Would someone, Marva, would like to talk a little bit about this thing of killing the virus on the filter?
The virus is trapped by the filter, right? I don't think that we are in the business of what happened to it, as long as it's trapped in the filter, and we know that the virus needs a host to survive. So it's not going to duplicate, and it's not going to live for long. And the rate of, inactivating the virus will depend on many different factors. But this is very important. So killing, disinfecting, purifying, cleaning, trapping, they all can be equivalent. And this has been used in the marketing, like, when we talk about active technology, inactivation, soldier, natural toxins, all of that. It's all like marketing gimmicks. What we want is to reduce the risk of transmission. And this can happen by simply trapping the virus in the filter. That's it. What happened later, I don't think this is in our business.
Yeah, there's been a misconception that viruses can reproduce on a filter like bacteria or fungi could, and they don't.
Yeah, that's the right way of handling it, actually, because that's unfortunately technologies are there which do talk of all things, and you need to live with them. Gautam, to you, we've been hit, must be in other countries also, with a lot of officials, a lot of people saying put off air conditioning. There are people who are saying stop recirculation. That's understandable from one small perspective. The people saying just stop air conditioning. If you want to open your place, a public space or your personal home, just stop air conditioning and open your windows and run the fan. Most of the public spaces won't even have a fan, won't even have windows nowadays in the modern designs. How do we get and explain to these people that, listen, that's not the way out of this problem. In fact, that's maybe going to further add to your problem. So what do you see, Gautam, going ahead, the way of handling this?
Can you be a little more specific? You're talking in terms of public address or for...
Let's talk of public places. Let's talk of public places where people have been saying, don't run air conditioning.
It's a very difficult question to handle in terms of public spaces because of the, what has been going on in the past is that, it is the public spaces that have been the cause of all, the propagation of this virus. Okay. So you're talking in terms of those kind of spaces because all the history that you find that, it's been mainly the public spaces that have been, responsible for the propagation of the virus. Maybe your question would be in terms of whether air conditioning is safe even otherwise. I won't specifically, dwell on the public spaces. Air conditioning can be safe only if there is, adequate ventilation, there is adequate filtration, and that's about it. And your air patterns, what Dr. Kankari has been talking about, your air pattern, you don't want to be, sitting direct in line of fire of the virus coming out of another person, But these are concepts which are very difficult to convey to the people at large, I do admit. And I think it's only these kind of forums, I don't know how far it will reach, that can dispel these kind of, doubts. There was one particular question that was posed to me, is there a way of reassuring the people inside a space whether the space is, safe or not? That might be more in tune with answering your question. When they enter a space, is that space safe with the air conditioning? The only way you can answer it is, not with all these kind of diagrams and telling, the people that, this is what we have done, so this place is safe. The right way is if you have a way of having some sort of a real-time monitoring where you can show that, the virus is not there in the samples collected, and that's why this space is safe. And I believe that there is, in fact, a company, I think it is Smith or something like that, which has come up with this particular device with sensors, which is showing that, within 2 minutes, they've shown it at the University of Maryland, the real-time results, that the space is safe or not. And they're looking at, means of making commercial production of these kind of meters. So it's only when real time you can show in the air-conditioned spaces that, you are not having the virus, people will be reassured. And no amount of our saying that there is UVGI here or, some other filter there is going to reassure them. That's the fact of the matter. Thank you.
Can anyone add to that? That are we in a position or reaching that position of being able to detect the presence of the virus inside a space?
Yes, in fact, there is a company which has, I think in April, they have already come up with this particular sensor. It has been, as I told you, tested in 2 universities in US. One is University of Maryland, and it gives real-time results. That is, of course, 2 minutes delays there, and the results are equivalent to a PCR testing result. So it's that sort of, testing that they are talking of, and they're looking at commercially making it available. Only when you have this kind of a monitoring available, it will be like we talking in axioms that, okay, you've got UVGI, so this is safe, or I've got HEPA, it is safe. It's not that. People will need to have the proof of the pudding.
I wonder what
this
you'll do.
This is where what we're doing is absolutely key, in my opinion. by our continuous monitoring of not just particles, but of the whole consortium of indoor metrics that are influential not only to the levels in the building, but also to the human health impact of the interaction of those metrics. And it's exactly what you just said. It's real-time continuous monitoring, but then our data is fed through a health-related algorithm so we can say to somebody, yes, your building is safe, your building is not safe. But the other part of that question that I heard was, are we measuring, for example, in our system, quote unquote, viable organisms? And there are real-time bioluminescent technologies out there that detect the components of viable organisms. But unless you do like PCR or gel plate sampling, you're not going to get the true viability. However, we can choose surrogate particles and other conditions that would foster the presence of pathogens. And we can monitor those components of the indoor air continuously and affordably and relate them to human health, because I think that's exactly what we need, a lens to human health. And we can't achieve that through our monitoring.
Yeah,
So I think that's a bigger part of the
There's a
bill.
product on the market that was first announced last fall, and I've heard about it again recently. And it's essentially a lab in a box, and it will do the signature on SARS-CoV-2. When I saw a price for it, it was $19,000 US per unit. So that's a fairly high cost to put in every room in a school. And then the question is, what do you do if you detect SARS-CoV-2 in a room? Does that mean you shut down the building for 2 days to clean everything? We've got to figure out there's a principle in instrumentation measurement that you shouldn't measure anything unless you know why you're doing it and what you're going to do with that information when you get it. If we use these kinds of devices during flu season and we find influenza virus, do we do the same thing? They came up with anthrax too. So, it's really, I think we'll have those sorts of things someday, and they maybe won't have consumables, but then we have the question of what do we do when we detect a biological contaminant in a building?
So that technology, I mean, we do have that monitoring capability, Bill. But your question about what do people want to know and what do we do with the information is important. But there are some broad buckets of remediation that exist, and you have touched, this panel has touched on some of those. So I don't think that the sensing capability is in the future. We're doing it now. But affordable viability monitors are not quite there yet, but we have good.
Yeah, I was talking about practical systems, $20,000 components.
Well, our systems are about $1,000 or $1,500 per sensor pack, and then there's the data analysis. So it's certainly not $100, but it's not 80,000 either.
I wholeheartedly support this whole thought of monitoring, but there are so many things about this. If you put the sensor in the return duct and monitor the whole environment from one sensor in the return duct, my nose is not in the return duct. I'm breathing at the breathing zone. You are monitoring everything, which will very well kind of quantify your equations of dilution in the return duct. That's where they're well mixed. They're not well mixed at the breathing zone. So that's one point where we monitor it. The second thing is indoor air quality should be fundamental human right, because it's not about the philosophy, it's not about the textbook, it's not about ISHRAE or ISHRAE. It is about the fundamental human right. And if we want to do that, we need to create an active consumer of our design. Today, people are passive consumers. If their cell phone stops working anywhere in the world, they find the nearest cell phone store to repair it. If I go to the restaurant, I feel cold. Oh, I'm just here for 10 minutes or half an hour to eat my meal and I'm out of there. We don't have courage to call the manager and say, you know what? I'm cold here. I'm not comfortable. If I get sick in my office space, do I have courage to go to my manager and facility manager and tell, can you please check indoor air quality that is causing me the illness? We don't have that awareness. So the first thing we need to do is to create the active consumer of our design and automatically everything will fall in line.
And
That's
that's an interesting point, Kishore, about the consumer. And I think that it also, that point extends beyond COVID to, and beyond temperature and things that we can detect in the indoor environment, because many of the things that actually impact our health, both in the acute and chronic time scale, are things we don't even sense. And I'm not just talking about dry air, but particles and VOCs that diffuse through our skin and are as impactful as many inhaled components. So I think creating the visibility that we don't have with our five senses, and like you said, then we need the ability to manage buildings to remediate. And what you just said about who the consumer is, I think is a very important question.
No, I think that's hitting it right on its head, that we are still not bothered about the indoor air. Wherever we go to a restaurant, we will ask 5 questions about the quality of water we are being served. Is it filtered? Is it treated? Is it river RO? We've never bothered to ask about the air wherever we might go. And I think that is the only way this industry is going to change and recognize, because finally the person who owns the space needs to understand that the person visiting my space will only now come if he or she is satisfied with the air quality inside, whether it's the monitoring, whether it's the interventions, whether it's whatever technologies we discussed today or will come tomorrow. As long as the occupant or the visitor is not bothered, I do not think it will work on. Unfortunately, I'll have to draw this to an end because we've gone near half hour overboard, and with all of your very tight schedules having ahead with multiple other work on presentations coming your way. So I would now firstly thank you all of you. But I'm leaving this task of saying a good thanks to Mr. Chandrasekhar, N.S. Chandrasekhar, who is the incoming president of ISHRAE. And over to you, Mr. Chandrasekhar.
Thank you, Vishal. And very good evening, good afternoon, good morning to everybody who is present here. Wow, I think this is a great panel and great discussions, great presentations from all of you. Such a good, lively discussion. And one thing I'm sure, this discussion has thrown us to have more panel discussions, because this panel discussion has thrown open so many questions. And I'm sure we all are going to go back to our research books and find more answers to these questions and then come back with more panel discussions. That's the way it is going to be. I see that this panel discussion evoked a lot of interest worldwide. Close to 1,500 registrations we had on this for this, and we had a full house today. 500 was our limit as far as this on this platform. We had a full 500 house, full numbers present right from the beginning, and there were more present on the Facebook Live. We were transmitting live on the Facebook, and many more joined on the Facebook Live. We had participation from over 40 countries. We had delegates participating who are maybe consultants, contractors, suppliers, who are researchers, interested people in this field, from various associations who are partnering, who have got a memorandum of understanding with ISHRAE, and so many people have participated in this, and there can be nothing more fruitful to these people who have enjoyed, I'm sure, having spent a lively technical knowledge interaction. That's the more important part of it. I can't thank enough all these panel who have been here. Dr. William Bamfleth, you talked about the role of ventilation in mitigating the risk. You took us to inhalation exposure, increased ventilation. Thank you very much for being present here with us today. Dr. Marva Zatari, you talked about air cleaning, filtration, particle air cleaners, and also you talked to sticking with the proven technology. That was a real catchy phrase you mentioned. I'm sure there will be many takeaways for that. Thank you very much, Dr. Marva Zatari. And then we had Dr. Keshav Kankari talking about airflow patterns, which we all know very important, but many people don't realize that importance of it and then do, because we always believe air coming from one direction will always come definitely into the space. It will automatically come. That's the thought process which is there. But then how wrong that is our thought process. So you took us through the importance of air distribution. Thank you, Dr. Keshav Kankari. And then Dr. Stephanie Tyler took us through the humidity control and indoor environment, and I got a new words, which is today I will definitely study more on this, which is the health impact rating score, which is very, very important. And I'm sure every one of us have to realize this. Thank you, Dr. Stephanie Taylor, for being part of us and sharing your views. And then we had our own Gautam Baliga. I call him Dr. Gautam Baliga because he is our health TG group expert in this, in the healthcare. And then he did very good information on fast track and emergency facilities for tracking COVID-19 patients in India. So this is the way we want interactions. And I'm sure every audience who are present here really enjoyed this year. All this due to the effort of our effervescent Vishal Kapoor, who has, with his team of Nivedita and the back-end support team. We have a good back-end support team which have made this today possible. And I thank the president of ISHRAE, Amitabh Basur, for being present here in the beginning and then being there right till the end, listening to this lively discussion. It's really heartful. That's the way we feel after attending this thing. Thank you, gentlemen. Thank you, everyone who has been present here. And let's all go back thinking that our minds are really full with a lot of thinking to do, a lot of information which we have gathered, a lot of implementation to do. Thank you all. Have a good evening or a good afternoon, or have a good lunch or a good dinner, whichever way it is. Thank you.
Thank you. Thank you very much. Thank you, everyone. Thank you, the audience also.
Thank you. Have a good rest of your day.
Thank you. Thank you, everyone.
Bye.